This is our modelling motion lesson number 5. We're going to look at Newton's second and third laws and talk about momentum, weight, action and reactions, and friction. So the content in particular, explore and apply Newton's second and third laws, calculate momentum and change of momentum of a particle, explore and define normal and reactive forces, and solve some problems regarding friction. Newton's second law. When viewed from an inertial reference frame, the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. That is, acceleration is proportional to the sum of the forces divided by mass, which in turn is our formula F equals ma. Momentum. The momentum of a particle is defined as the product of mass and velocity. So momentum is mass times velocity. Example 20. Determine the momentum of a 110 kilogram object moving at 86.4 kilometers per hour. So state the mass and velocity. The mass is 110, velocity is 86.4 kilometers per hour. Convert to meters per second. That is, multiply by 1,000 and divide by 3,600 seconds. That is 24 meters per second. Recall the momentum formula, which is momentum equals mass times velocity. We can evaluate by multiplying mass times by velocity. And that's 2,640 kilograms meters per second in the direction of travel. The change of momentum is central to Newton's second law of motion. Its importance is introduced through the following example. That is, the change of momentum, delta P, can be expressed as m mass times the change in velocity. Example 20. Calculate the change of momentum of a 30 kilogram object decelerating from 60 meters per second to 20 meters per second. Recall the rule, delta P equals mass times change in velocity. Substitute in the values. A mass is 30 and a change in velocity is 20 take 60. Evaluate and include units. Change momentum is negative 1,200 kilograms meters per second. Newton's third law. If you press your finger against your laptop with your fingertip, the laptop pushes back and makes a small dent in your skin. If you push harder, the dent in your skin is a little larger. This illustrates those forces are interactions between two objects. When your finger pushes, the laptop pushes back. Newton's third law. If two objects interact, the force F from 1 to 2 exerted by an object, by object 1 on object 2 is equal in magnitude opposite in direction to the force F21, which is exerted by object 2 on object 1. That is, our force exerted by 1 to 2 is equal to negative force 2, 1. Often the two forces are called action and reaction forces. Weight. The gravitational force per unit mass due to the Earth is G newtons per kilogram. It varies from place to place depending on where you are exactly on the Earth, not by much. A mass of mkg on the Earth's surface has a force of mkg weight, which is mass times gravity newtons acting on it. The force is known as weight, where mass times gravity is weight. Reaction forces. Consider the laptop resting on the desk. The forces acting on the laptop are the normal force, reaction, N, and the gravitational force, weight, which is mg. So a laptop, we have weight, which is mg, and a reaction force, which is called the normal force. In such a situation, we have the normal, which is our reaction force, being equivalent to mg, which is our weight. Note, technically, this is not Newton's third law, as they do not represent an action-reaction pair, because both forces act on the same particle. Example 21. Determine the weight of a 120 kg person sitting on a chair and the normal force from the chair onto the body. State the mass, which is 120 kg. The formula for weight is mass times gravity, mass times acceleration. We substitute in values and evaluate. So 120 times 9.8, it's 1,176 newtons down. State the equivalence. The magnitude of weight equals the magnitude of the normal reactive force. Hence, the normal force magnitude is 1,176 newtons. And that would be up. Friction as a force. An object moving across a rough surface will be opposed by a resistant force due to friction. So we have our weight and our normal, and our velocity and our friction force opposing it. This force opposes the velocity of the object and depends on the friction coefficient and the normal reaction force. Friction as a force is given as mu times the normal force, where mu is the coefficient of friction. Example 22. Calculate the minimum friction force required to move an 8 kg object along a horizontal surface with a coefficient of friction of mu equals 0.6. State the given information, our coefficient of friction and our mass, recall a rule and express the normal force as a weight. So our rule for friction is mu times the normal force, and our normal force is directly opposing the weight, which is mg. So sub in our values, our mu is 0.6, our mass is 8, and gravity is 9.8. Hence, if we evaluate, that frictional force is approximately 47.04 newtons. Example 23. An object of mass 8 kg rests on a rough horizontal plane, is pushed by a horizontal force of 20 newtons for 7 seconds. Frictional force of the object we're moving is 16 newtons. So you've got one direction, it's being pushed by 20 newtons, and the force opposing it is 16 newtons. Calculate how far the object travels in the first 4 seconds. Calculate the net horizontal force. So using F equals ma, we want to work out force, the net force. We've got 20 in one direction, the positive x-axis. Take away 16, which is our friction, so our net force is 4i. We divide both sides by 8, our acceleration is 0.5 meters per second squared. Determine the velocity, we can integrate acceleration in terms with respect to t, that gives us 0.5 t. We can find displacement by integrating velocity, and that would be, using the power rule, 0.5 t squared divided by 2, which is a quarter t squared. After 4 seconds, we can sub in 4, so 16 times a quarter is 4. We travelled 4 meters after 4 seconds. Let's revisit Newton's second law, which is F equals ma. Example 24. A bike accelerates from 2 meters per second to 20 meters per second uniformly in 6 seconds. Determine the bike's acceleration and the net force on it if its mass is 64 kg. So acceleration is delta v over delta t. So we've gone from 2 to 20 in 6 seconds. That would be 3 meters per second squared as the acceleration. Now recalling our second law, which is F equals ma, a net force would be our mass, which is 64, times the acceleration, 192 newtons was required for that situation to occur. Now to test your understanding at the end of our lesson 5, have a go at the following 2 questions. And we'll only have one lesson left, which is lesson 6 on modelling motion.